All right. So we have several units in the concentration. Sorry. And the molarity, which is the mole of solute divided by the liter of solution. So we have the molality, the mole of solute divided by the kilogram of solvent. We have also normality and also part per million ppm, which is a milligram of solute divided by the liter of solution. Part per billion microgram. Microgram of solute divided by liter of solution, and also percent concentration, which is the percentage of weight by volume, and also volume by volume. Now, the most commonly used concentration in analytical chemistry is the molarity, the first one. Molality is rarely used, and instead of molarity, we also use part per million, part per billion, and as well as percent concentration. The percentage of weight of solute divided by weight of solution, percentage of weight of solute divided by volume of solution, and also percentage of volume of solute divided by volume of solution. Right? So molarity, okay, the most commonly used one is number of mole of solute divided by the liters of solution. So it is mole per liter. Okay. While the molality, we not really use this one, molality, number of mole divided by kilogram of solution, right? And this is the example, as you can see from the note that also given to you. Okay. The question is, what is molarity of salt solution when 0.6 gram of sodium chloride dissolved in 100 ml of water? So given that the molecular weight of the sodium chloride is 55.5 gram per mole. So how to calculate it? Remember, molarity is about number of mole divided by liter of solution. So we need to know how many moles, okay, inside 0.6 gram of sodium chloride. So how to do it? We times, okay, the gram, okay, times the what? Is it the molecular weight? I need to times gram times molecular weight. Am I true? The first step?
1 over molecular weight.
What? Is it times or divide by molecular weight?
Divide,
How to
okay,
calculate
divide.
the number of mole? All right, so you got the gram and you got the molecular weight. What you need to do is, again, divide all times. You have 0.6 gram, and you have the given that is 58.5 gram per mole. You need to divide. Am I correct?
Divide the molecular weight.
All right. So that after that, what need to do? You have the number of mole now, right? So what you want to know is the molarity, which is number of mole divided by the volume of water, which is in liter. So 100 ml we convert into liter. So how many liter? 0.1 liter. So we get 0.60 mole per liter, or 0.60 we call as molar. We call as the acronym, the short form of molarity is molar. Okay. When somebody said 0.1 molar, meaning that it is 0.1 mole per liter, right? Okay, now, what is the molarity of a solution prepared by dissolving 8 gram of sodium hydroxide in water so that the final volume is 250 ml? Okay, now you need to find the molecular weight of sodium hydroxide by yourself. Okay, And then try to find what is the molarity of 8 gram of sodium hydroxide in 250 ml of water. Come on. This is kacang one. Okay, come on. Who found it? Who got the answer? Got the answer? How many molar? Guys. 2.67 from Ng Wei Fu. And from somebody else? How much? Come on, you have calculated or not? Ng Wei Fu, can you share with us how you calculate it? Come on. How many? What is the molecular weight of sodium hydroxide?
Oh, sorry to that. I think I used the wrong molecular weight. I used the water one.
All right. So it's not water, right? So you need to add sodium molecular weight and oxygen molecular weight and hydrogen molecular weight. Okay. Logaraj, you got 0.8. All right, come on, share with us, Logaraj, how you calculate it?
8 grams times with 1 over 40. 40 is the molar weight of nitrogen monoxide, then times with
Okay.
1 over 250 times 10 to the power of -3.
So everybody got 0.8 molar? Is it correct? All right, good. Okay. All right, so concentration in terms of percent composition. So that I mentioned previously, there are concentration that in percent of composition. So the concentration of substance in commercial aqueous reagents, such as the organic solvent, commercial household products, are usually expressed in percent composition. Okay, for example, weight percent, which is percentage of weight by weight, meaning that weight of solute divided by weight of solution times 100. Okay, and then we have volume percent, which is volume of solute divided by volume of solution times 100. And we have also weight volume percentage, which is the weight of solute divided by volume of solution times 100. Okay, but normally we use percentage weight by weight and also percentage volume by volume. Okay, for example, there you can see in the note 37%. Okay, 37% of hydrochloric acid. Okay, meaning that 37 what's that? Oh, what is that? Okay, that is volume by volume. Okay, so 30%, for example, 30 if the solution, the total of the solution is 1 liter, so it is 370 milliliter of hydrochloric acid, and also 630 milliliter of water, right? And then you have the salicylic acid shampoo, 6% weight by weight, and the total volume is 177 ml. So my question is, what is the volume of salicylic acid in the shampoo? Okay, put in the chat your answer. What is the volume of salicylic acid in the shampoo if the total volume is 177 ml? Okay, that if the if the if the percentage of hydrochloric acid is by week by week, so 37% labeled in on the HCl reagent bottle, meaning that 37 gram HCl per 100 gram of solution. If it is volume by volume, so similar way to calculate it. Okay, so 10.62 mil, 10.63 mil, I think approximately that amount, right? 10.62, 10.63, right? Same. Okay, so you got the answer. Okay, you know how to calculate. Okay, guys, you know how to calculate it? Okay. Right, so eye medication, this is 0.05% HCl ophthalmic solution. Okay, so weight by volume percentage. Okay, what is the weight percentage of a solution on 0.05 gram epinestine in in 100 ml of solution? So you calculate it, you got 0.05% weight by volume. It is example of 33% of hydrochloric acid, right? How many of hydrochloric acid needs to be added into 100 ml of solution to prepare 33% volume by volume? Of course, it's simple question. So you need to put 33 ml, right? So some shark can detect odors, mostly from blood, at concentration of 1 part per billion. Okay, now we come to part per million, part per billion, and also part per thousand. Okay, normally known as ppm and ppb. When I say ppm, it will mean part per million. When I say ppb, it will be part per billion. All right, and ppt can mean 2. Okay, which is the part per thousand or part per trillion. Okay, so the shark, okay, shark can detect a concentration of blood, okay, at the concentration of part per billion. So how much is part per billion? Just how small is part per million or a part per billion? You just imagine in one Olympic size swimming pool, which consists of 660,000 gallons, right? So the part per million, meaning that 1.25 2-liter bottles. This is 1 part per million of soda in one Olympic size swimming pool. That is 1 part per million. And what about 1 part per billion? Imagine you put half teaspoon of the soda into the Olympic size swimming pool. So that is 1 part per billion, right? Can you imagine now how small the concentration is, right? But don't be don't be shocked that some of our modern instruments can detect the concentration at 1 part per billion. Okay, later on we will learn about that instrument. Okay, so million is 1 with 6 now. Okay, 60. Okay, what about billion? We have, well, how many there? Okay, 90. What about trillion? We have 12 0. Okay, so that is basic thing about million, billion, and trillion. Okay, so 1 to the power of 10 to the power of 6, 10 to the power of 9, and 10 to the power of 12. That is million, billion, and trillion. Okay, so 1 part per million, meaning that 1 in 10 to the power of 6. 1 part per billion, 1 in 10 to the power of 9, and 1 part per trillion is 10. So 1 in 10 to the power of 12. So part per million is most common one we use in analytical chemistry. So 1 unit volume in 10 to the power of 6 unit volume. So blood in ocean. Okay, 1 unit mass in 10 to the power of 6 unit mass is mineral in solid. The example is, okay, the example of the concentration. Okay, if it's in volume unit, you just imagine blood in ocean. If in mass unit, just imagine mineral in solid, right? 1 unit mass in 10 to the power of 6 unit volume, just imagine salt in water. Okay, what is the approximately? Just imagine that swimming pool size, okay? Olympic size swimming pool, and put 1¼ bottle, that is one part per million. If you put half teaspoon, that is 1 part per billion, right? So commonly used unit is ppm, which is part per million. So gram of solute, okay, the unit is gram per solute divided by gram of solid times 10 to the power of 6. Okay, that is ppm. Okay, therefore the unit is microgram per gram. Until this part, do you understand that why we use ppm equal to 1 ppm equal to 1 microgram per gram? Okay, because part per million meaning 1 divided by 10 to the power of 6. So that if the unit is gram, so 1 gram divided by 1 million gram. So if we do some of the calculation, okay, so it is 1 microgram per gram. So it is equal to 1 microgram per gram, or 1 milligram per kilogram. So it equal to 1 gram divided by 1 million gram. Okay, so this the unit for ppm is equal to 1 microgram per gram, or 1 milligram per kilogram. Right, now come to example. A 2.6 gram of plant tissue was analyzed and found to contain 3.6 microgram of zinc. So what is the concentration of zinc in the plant in ppm? Okay, 2.6 gram of sample of plant tissue was analyzed and found that it contained 3.6 microgram of zinc, meaning that 3.6 microgram of zinc in 2.6 gram, right? So the concentration is, when you calculate, 1.4 microgram, or it is ppm unit. Okay, guys, understand? Understood now? Understood? Give thumb up.
Yes, doctor.
All right, so the simple one, right? Okay. So what about 1 unit mass in volume? Okay, in 10 to the power 6 unit volume. The example is like you put 1 teaspoon of salt. One and quarter, or 1 or 2¼ like the example previously I showed you, right? Okay, 1¼ to 2 liter bottle of soda bottle inside the 1 Olympic size swimming pool. So that is 1 ppm. All right, so 1 ppm of salt in water is 1 gram divided by 1 ml times million, 1 million, or 10 to the power of 6. So it is equal to 1 ppm. Okay, so therefore the unit is 1 microgram divided by 1 milliliter. Okay, or equal to 1 milligram divided by 1 liter. Do you understand why it become like this? Okay, because we just we just change the unit. Okay, the ppm is 1 gram divided by 1 million milliliter. So if you divide, or sorry, if we change the unit, okay, from to another form, so it is equal also with 1 microgram divided by 1 milliliter, or 1 milligram divided by 1 liter. So that is equal to 1 part per million unit of mass in volume. All right, for example, it is stated that the lotus infusion oil and cream ceramide, okay, is 2000 star. Okay, then cream. What does it mean? Right? Okay, look at the bottom one, 30 mil divided by well, the unit is mixed now. They use it also oz. What is oz? Oz is ounce. Ounce unit. Okay. So we go to next example. A 0.25 ml of serum sample was analyzed for glucose content and found to contain 26.7 microgram. Okay. Calculate the concentration of glucose in ppm. So 26.7 microgram. Okay. How to do it? So please calculate for a while. 26.7 microgram, okay, in 0.25 milliliter. So you just change to ppm. Okay, how many ppm? Remember the unit of ppm. 1 microgram per how many liter, milliliter or microliter or what? And then equal also 1 milligram per how many liter? So now what is the ppm? Remember ppm, it can be 1 microgram per milliliter or 1 milligram per liter. So how much is it? How many ppm? How many ppm? Concentration of glucose. Do you understand? Simple one, right? How many ppm of glucose in the serum sample? How many ppm, guys?
Is it 106800?
So just divide 26.7 divide 0.25. How much you got?
106.8.
Microgram per milliliter also can. And also if you want to change it, also you can change to milligram per liter. So it is directly divide. So you got 106.8. Right, good. So that is ppm. Or you can write as milligram per liter or microgram per milliliter. But normally we write milligram per liter. Right? Next. Okay, the percentage week by week unit may also be expressed as a fraction. Right? Example, 37% week by week can be expressed as 37 parts per 100. How about the smaller fraction? Okay, part per 1,000 or part per million. When the sample is in liquid form, we can use week by week percent in volume as well. And how is it? Right? So as the density of aqueous solution often very close to 1 gram per liter, we usually correlates 1 gram water with 1 ml of water approximation. So therefore 1 ppm also equal to 1 microgram per gram can also be converted to 1 microgram per milliliter. So because approximately, okay, the density of water is 1 gram per liter. So we can change 1 gram to 1 ml of water. So we can change gram to milliliter. So 1 microgram per gram also equal to 1 microgram per milliliter. Right? Understood until this stage?
Yes, Doctor.
All right, good. For trace analysis in liquid sample, analysis for very little amount of analytes. It's part per billion and part per trillion. Okay. So similar with part per million. Okay, part per billion can be 1 nanogram per gram or 1 nanogram per milliliter or 1 microgram per liter. What about part per trillion? Oh, this is really small. So part per trillion is 1 picogram per gram. I believe some of you never heard about picogram, right? Picogram. 1 picogram per gram or equal to 1 picogram per milliliter or 1 nanogram per liter. We rarely use this one. Okay. There are also some example to convert percent composition to molar concentration. Right. You try to do this example. A commercial aqueous ammonia, NH3, water is labeled as 28% weight by weight and has a density of 0.899 gram per mil and molecular weight of 17.03 gram per mole. Let's say you want to convert the concentration into molarity for easier calculation in your lab book. How can you do that? Remember, molarity is number of mole divided by liter, right? So now you have the molecular weight, okay? You have the percentage and you have the density, okay? So how you come up with the molarity, okay? So how to do it? The first one, okay, because it said that 28% weight by weight, so 28 gram per 100 gram times the density, okay, and we time density, so you got the percentage of gram, sorry, the percentage of weight in volume. So you got 0.2517 gram per mil, okay? And then after that, you just imagine you just cancel, okay? When you times, you cancel gram and gram, so now you got gram per milliliter. So now you got the percentage of weight by volume, 0.2517 gram per mil. And now we divide by the molecular weight. Okay, when we divide by molecular weight, so we got now concentration become molarity. So we have 0.01478 mole per milliliter. Okay, but molarity is mole per liter. So how much is 1 mil? Okay, when we convert to liter, so now we got 14.8 molar of the ammonia. Okay, molar. When I mean molar or molarity is mole per liter, or just labeled as M. Okay, you got it, guys? You got it? How to convert the percentage of weight by weight to
Yes, doctor.
to molarity. So because it's given there molecular weight, we just convert it to with the density. So we got the weight by volume. So now with the weight by volume, we divide by the molecular weight. Now we got the molarity, but we change the milliliter to liter. Now we got the real molarity unit. So now preparation of solution. How to prepare 250 ml of 0.1 molar sodium hydroxide from sodium hydroxide solid. And given that the molecular weight of sodium hydroxide is 40 gram per mole, right? First, you calculate the weight of sodium hydroxide pellet using molecular weight to produce 0.1 molar solution, okay? And then you need the calculation there, okay? You need to know the weight, okay? And then you just weigh the sodium hydroxide and dissolve it in water approximately, okay? With rinse, okay, you need to rinse all the, this is a wet lab, okay, situation. After this, you need to prepare in the lab, okay? You need to weigh the sodium hydroxide pellet, dissolve it to the certain or exact volume to prepare the exact concentration. What is the apparatus there in the photo? What we call that? The one that looks like a conical flask, but you have the mark there for the exact volume. You have this topper, right? When you put the solution inside the apparatus given in the photo, and you put the solution up to the mark, and it is now being in exact volume. So what we call that apparatus? What we call that? Anybody recognize what's that? With the green solution inside it? It is used to prepare exact concentration of a compound. Okay. For example, sodium hydroxide, we need to dissolve a certain amount of sodium hydroxide inside it and put water up to the mark for exact volume. Now we got the exact concentration that we want to prepare. What is it called? Anybody recognize what is that? Come on. Just try to answer.
Round
What is
bottom
that? Round bottom?
flask.
Round bottom flask.
Is that
Okay,
right?
round bottom flask. Okay.
Volumetric flask.
Volumetric flask. Okay, that's good. Okay. So what we call that? A volumetric flask. Okay. Also called a round bottom flask, but also exactly we call as volumetric flask. Okay. Volumetric flask meaning that we have that exact volume. Okay. For the apparatus, we need to prepare a solution. That is how we do it. So we calculate, or we weight a certain weight of the salt or the any compound that dissolve in water to prepare the exact concentration. For example, we want to prepare 0.5 molar. Okay, we calculate how many of sodium hydroxide that we need to put, and then we weigh it, and then we put in the round bottom flask or volumetric flask. Okay, and then we put the water up to the mark. Now we have the exact concentration we want to prepare, which is the 0.1 molar. Okay. All right. How to prepare 25 ml of 0.0 molar glutamic acid solution from glutamic acid powder. Okay. So the molecular weight is 147.13 gram per mole. Okay. Okay. How much glutamic acid powder that we need to put in 25 ml of volumetric flask? How much? To prepare 0.1 molar. 0.01, sorry. How much? Calculate. How much, guys? You have calculated? Guys? How many gram of glutamic acid powder you need to take to prepare 25 ml of 0.01 molar glutamic acid solution? Come on, come on. 0.0368. Zero point 0.037. Okay, that's approximately that amount. Okay, 68 or just 368 or just 37, right? Okay, good, everyone. Now you understand. Now it comes for the dilution of the solution. Okay, the mantra that you need to remember always in dilution is M1 V1 M2 V2. Okay, so what is M1, what is V1, what is M2, and what is V2? Okay, N1 V1 equal to M2 V2. So M1 is the concentration of the original solution, and V1 is the volume of the original solution. M2 is the concentration of the diluted solution, and V2 is the volume of the diluted solution. So if let's say you have 1 molar of original solution. Now you want to prepare 0.5 molar of the solution, okay, in 100 ml. Okay, meaning that you need 100 ml of 0.5 molar of that original solution. Okay, so what is the volume of the original solution that you need to take to put it in 100 ml of water, let's say? Meaning that to put in the volumetric flask up to the 100 ml, okay, what is the volume of the original solution from 1 molar to 0.5 molar? Anybody can answer the question? M1 V1 M2 V2. So just put directly in the equation so that you know how many of the original solution that you need, okay, to prepare the diluted solution. That is the mantra that you need to always remember in analysis, in instrumentation as well. You need to prepare the calibration solution. You need to prepare a several concentration of calibration solution. So this is a mantra that you always need to remember. If you have the original solution, okay, normally the original solution is more concentrated than the diluted one, of course. Okay, then how much of the original solution that you need to take to prepare? This is a mantra that you need to always remember. Okay, this is a formula, right? 100 molar. So we diluted to, it is diluted to 10 molar and diluted to 1 molar, diluted to 0.1 molar and 0.01 molar. So how many is the dilution factor is that? How much dilution factor is that? So the dilution factor is 10, right? Right. This is the example. What is the volume needed to prepare 2.5 liter of 0.36 molar of sulfuric acid, starting with concentrated acid that is 18 molar. So M1 V1 M2 V2. So we have M1 18 molar. We don't know how much to take of the V for 1, and then we know that we need to prepare 0.36 molar with 2.5 liter, the final solution, right? The diluted solution. So we found that V1 is 0.05 liter or 50 milliliter. So this how we use this formula to prepare the diluted solution. How much of the original solution that we need to take to prepare the diluted solution. Okay, now, right? Now I want to call you randomly. Why do we need to do serial dilution in chemical analysis? Right? Why do we need to do serial dilution in chemical analysis? All right, the first one I need to know from Abdul Rahman. Abdul Rahman, are you here?
Yes, doctor.
So why we need to do serial dilution in chemical analysis from your idea?
I believe that it will help us to precisely know about the chemical we need to know.
You got the idea a little bit. Okay, next I want to know from Hafika Siddiq. Hafika, are you here, Hafika? Hafika, come on. Why do we need to do serial dilution in chemical analysis?
Get the required concentration.
Why? To get what?
The required concentration.
To get the required concentration. Yes, okay. Also a good answer. Right, and then Nur Muhammad Aiman. Where is Nur Muhammad Aiman? Aiman, where are you?
Yes, doctor.
So why we need to do serial dilution in chemical analysis? Why we need to do M1, V1, M2, V2?
I think to estimate the concentration.
To estimate, not so accurate, but okay, good try. And Sarveswaran Tiagu. Sarves, why we need to do dilution in chemical analysis?
To estimate, to get a more accurate representation of the concentration.
Okay, got some idea. And So Rui Sheng. How to pronounce Rui or Rui? Okay, So Rui Sheng.
Either way is fine.
Huh?
Um,
How to pronounce your name? So Rui Sheng.
to be honest, I don't know too. So you can go whatever you want.
Okay. All right. So why we do this? Why do we need to do serial dilution in chemical analysis?
The thing is that we can calculate the concentrations of the sample that we examine.
Calculate what?
The concentrations of the sample of that we examine.
Okay. You got. I think you got the point. Okay. So good, guys. Thank you. Right. So this is why. Okay. You need to remember this very important thing that you need to tell you. Okay, I believe. Okay, this is the end part of this lecture for today because it is 10 o'clock already, 10 p.m. already, right? Okay, guys. The thing that we need to know is, okay, after this we're gonna learn about instruments. Okay, remember like the first class I told you we have to learn in this class two main techniques or methods in the instrumentation. The first one is spectroscopic, based on a spectrum. You have know the idea. Previously, I have asked you spectrum or light. Okay, the instrument based on spectrum or light. Okay, and then the another one we have the instrument based on the chromatography or separation technique. Right? Remember, guys. Okay, who create this instrument? Who invent this instrument to ease us in analysis? Who created? We create the instrument. Am I right? Am I right, guys? We create the instrument to help us to do a better, accurate and precise analytical, technique to detect the concentration of any analyte. Am I correct? We create the instrument. Human. Okay, we as human, we invent the instrument. Am I correct? Do you agree with me? Do you agree with me, guys? Okay.
Agree.
If you agree, respond it. All right. So we, as a human, we invent these instruments. Okay, to ease us in detecting the concentration of the analyte inside the sample, for example. Okay. Okay. Now, let's say our instrument is based on spectrum, meaning that the instrument can detect the spectrum. Okay. Various kind of spectrum. Okay. Now, let's say the instrument is there. already created by us, okay, already invented the instrument based on spectrum. Okay, now we have an unknown concentration of analyte inside the sample. We have a sample and we don't know the concentration of analyte inside it. And then we let the instrument to analyze the analyte inside it, okay, the sample. Okay, we let the instrument that we as human already invent, the instrument based on spectroscopy, okay, based on spectrum, which is named by AAS, atomic absorption spectrophotometer instrument, right? Now the instrument, is it can or should the instrument, could the instrument can tell us directly, oh, this is the concentration of the analyte inside the sample, just like that? Do you believe that the instrument that already invented, and then we put we rerun or we analyze any sample with that instrument? Let's say the instrument is based on spectroscopy, based on spectrum or light. Okay, when we analyze that sample, is it directly the instrument can tell us the concentration of the analyte inside it, just like that? It is just like that. Do you agree with me? Or can someone give your idea? Could the instrument tell us directly the concentration of analyte inside quantitatively? Remember, we have qualitative and quantitative. Quantitatively, the instrument can tell us, oh, this is 1 ppm of analyte inside it. Could the instrument do that directly? Someone, please, give your idea. You have 60 of you here, 60 or yeah, 58 right now. Okay, 57 right now. Okay, can the instrument tell us directly? That's answer from our friend, which is Naim. Naim, you said cannot. Why, Naim? Can you give your idea? Now we are in the learning process. It's okay. Don't afraid to to try. Don't afraid to say something that is not so accurate. Okay, because we are still in learning process. Naim, why, Naim?
Because I think we need to calculate it. We can get the concentration and
We need to calculate. Okay, Naim got the idea. We need to calculate. Okay, now let me tell you. Okay, as I said, we invent an instrument that can tell us the concentration based on the spectrum. So now the instrument only can detect how much or how, yes, because it is quantitatively. So how much is the light or wavelength absorbed by the sample that have been supplied by the instrument. So it is not the concentration, it is only the response. Okay, the instrument only know the response. Let's say the instrument is based on light. So the instrument only know how much the light is, how much the energy that being absorbed by the sample when it supplies some energy, and the same amount of energy absorbed by the sample, how much. Okay, and the instrument cannot tell us directly the concentration because they don't know how to calculate the concentration. Who knows to calculate the concentration? Can somebody tell me? Who knows to calculate the concentration? Come on, someone. Who knows to calculate the concentration in this situation? The instrument or us? Yes, we can calculate the concentration. The instrument only can tell us the response. Okay. Now, for example, the response of this instrument is absorbance. How much the energy that being introduced to the sample and absorbed by the sample based on the amount of the analyte inside it. Okay, the more analyte inside it, the more it absorbs the light that we introduce to the sample. So now The instrument only can tell us, oh, Mr. Naim, when you introduce the sample and when we supply the light to the sample absorb 50% of the light that we introduce. Okay. So Naim asked the instrument, okay, so how much is the concentration? I'm sorry, I don't know how to calculate the concentration. I only know how much the absorbance is, how much your sample absorb my energy, that the energy that being supplied by the light source. Okay, so remember all the student I taught analytical chemistry. This is the best quote I can tell you. All the instruments are stupid. All the instruments are what? I'm not rude here because we say that to the instrument. Okay, right. All the instruments are not clever. Okay, no Shahira, good one lah. Not clever. Stupid, daughter. Stupid is very rude lah. Okay, so all the instruments are not clever. Okay, who the one who should teach the instrument? We should teach the instrument. Okay, instrument, you already know the absorbance. Okay, you know the absorbance. So now I want to teach you. If you absorb this amount, if you can detect the absorbance of this amount, this is actually 1 ppm. And when you detect the absorbance of this amount, okay, this is actually 2 ppm. And this is 3 ppm, and this is 4 ppm, and this is 5 ppm. So you prepare an increasing concentration of the analyte, or we call as a standard solution. Okay. For example, you want to analyze a zinc, okay, zinc in your sample. So you prepare a 5 known concentration of zinc solution. Why 5? Because we can accept mathematically or statistically 5 different, or 5 increasing concentration, different concentration, right? 1, 2, 3, 4, 5, for example, and start with 0 lah. So prepare 6. Okay, 6 concentration. Start with 0, 1, 2, 3, 4, 5. So we teach the instrument. I know that you are not so clever. So this is the how you know the concentration. Okay, this I prepare this one is 0 ppm. So let's try how much absorbance of this 0 ppm of zinc. Oh, the instrument said that, oh, it is 0 absorbance. It is no absorbance at all. Yes, instrument, because there are no zinc inside it. Okay, now how much you absorb, how much you can detect the absorbance of this solution. Oh, I can detect some amount of absorbance. Okay, instrument, that is 1 ppm. And this is 2 ppm, 3 ppm, 4 ppm, and 5 ppm. Now you know. Okay. Okay, instrument says, thank you, Naim, because previously I only know the absorbance of the analyte. Now I know. So this is a concentration. Okay, nice one, instrument. So let me introduce you an unknown concentration of sample. So when the instrument detect the absorbance of unknown concentration, so because we don't know the concentration and instrument also don't know, but instrument know the absorbance of the zinc inside the sample. So when the instrument relate back with the knowledge that we told previously about the concentration, the instrument can detect. Look at the red circle. The instrument detect the absorbance is in the red circle. So the instrument directly relate with the knowledge of concentration that we taught previously, and they can convert it into concentration. Okay, this is actually a 1.3 ppm. Okay, good one, instrument, good one. But what happened if we introduce a sample with actually the absorbance is out of the range from 0, 1, 2, 3, 4, and 5 ppm. The absorbance is more than that. And the instrument also tell us some amount of concentration. Can we believe that value? It is out of 0, 1, 2, 3, 4, 5 ppm. And the instrument say that, oh, this is 6.5 ppm. Can we believe that amount from the instrument? Someone, please. Can we believe that amount? Can we use that? Can we report that? Come on. Come on, someone.
No.
Yes?
No.
Yes, yes, I can hear you.
We cannot believe the
We
what the
cannot
machine
believe
said.
what the machine said, the concentration, because
It's not accurate.
because
Because
because of what?
the spectrum detect other matrices.
The absorbance?
Yes.
The absorbance detect what? Detected at?
Other matrix. The number analyte.
Out of range, okay? The keyword is out of range. We only taught the instrument until 5 ppm, okay? The instrument just try and error. Oh, if relate back what based on what you told me, so this is 6.5. The instrument just draw the straight line, okay? Extend the straight line, but we cannot use it because in analytical or in statistic, we cannot use that because we haven't told the instrument yet about the concentration. So it is out of range and we cannot use the concentration that is suggested by the instrument. So how to do? We need to do another standard concentration, okay? More than that. Okay, if now we have 0 to 5, we extend it to maybe to 10 ppm. So now you have choice. Either you want to do the the standard solution up to 10 ppm, or you dilute the sample that is more than or out of range than what you told the instrument. Okay, so if you dilute it, it's better. You didn't, you don't have to prepare more standard concentration because you dilute your sample. So now it become more diluted, so it is in the range. Okay, you just estimate, okay, this is, I just dilute it by 2 times. Okay, and then you, because the instrument previously suggests is 6.5, so I dilute 2 times, so maybe the instrument can detect 3 something. Okay, logically. So when you run the sample, when you analyze the sample, is when it is detected at 3.5, so it is acceptable because in the range of the calibration calibration line that you have prepared. So the graph, okay, the straight line graph, the absorbance versus concentration, that is what we call as calibration plot. Okay, calibration plot. We have the equation there, y equal to 1.007x plus 00. This is y2. Y equal to mc 3. Y equal to what is straight line equation? Y equal to mx plus c, right? What is the equation actually? Y equal to the straight line equation, linear equation. Yes, mx plus c, right? So what is the m? M is a slope. Okay. And then what is c? C is the intercept. Okay. So this y equal to mx plus c. This what we call as calibration plot. So the only way that we need to teach, we can teach the instrument that only know how the instrument is not clever, like our friend Nur Shahira said, not clever, right? So the instrument only know the response. So we the one who need to teach the instrument how to know the concentration. So what is the method of teaching the instrument? Calibration plot. Okay, we prepare a series of standard solution of known concentration of analytes, and then we told the instrument how to define the concentration. Now we can analyze our unknown sample. Okay. Okay, class, got it? Any question about it? Especially on the calibration solution. This is where you need to do M1, V1, M2, V2. Okay, this is the application of M1, V1, M2, V2. Right, understood, class? If you have question, please open the mic and ask me. Everyone, you can understand? Because this is very important one in this part, okay? The preparation of calibration solution. After this, we're gonna learn a lot on the instrumentation. We're gonna use this technique, okay? All right, so good, you understand? Right, we have come at the end of the topic. So, right, we have a class activity now. Okay. Okay. Now, we need to do this thing. Okay. You are required to prepare working standard solution of 1 times 10 power of -5. Okay. What is the concentration? Okay. 2 times 10 power -5, 5, and 1 to power 10 power -4 molar alanine from amino acid from a 0.1 molar stock solution for trace analysis. Okay, it is a form of amino acid. Okay, alanine. You have only 100 ml of volumetric flask and pipettes of 1, 2, 5, and 10 ml volume. Outline the procedure for preparing the working standard and show any calculation involved. Okay, we must try this, and we're gonna discuss about this after this during our physical class. I believe this is the first and ever physical class that we're gonna meet. Okay, in N03, what? N03, or where was our class? Okay, so we will meet there next week, okay, to discuss about this, and we go to the next topic after that. Okay, class, that's all for tonight. Thank you so much. If you don't have questions, all right. So you are opening whiteboard. You want to teach us something? Viewing so Ray Shang whiteboard. Oh, you accidentally open whiteboard. I thought that you want to tell us any subject tonight, and then I'm ready to learn from you. Okay. Okay, so guys. Okay, Josh is just joking with us tonight. Sorry, I pressed it by accident. Okay, okay. I know. Okay. So thank you so much. Thank you so much for waiting for me. I just come back from Singapore for an exhibition tomorrow. I will go again to Singapore at 6 a.m. until 5:30 p.m. What a day for me for these 3 days. Very, very tired. Okay. So we'll meet next week. Okay, on our physical class. We have fun after that. Okay, during our physical class. Okay.
Thank
See
you,
you again.
doctor.
Bye bye.
Thank you, doctor.
Bye night.
Bye bye.
Thank you, doctor.
Thank you, doctor.
Okay.
Thank you,
Welcome.
doctor. Good night, doctor.
Sweet dreams, doctor.
Jaga diri, doctor.
Okay, thank you. Good night, sweet dream.
Doctor,
Yes, yes.